Our next speaker is Brett Cline from Codasip. Brett is the Chief Commercial Officer at Codasip, and spent time as Vice President of Sales at OneSpin, Senior Group Director of Customer Engagement at Cadence. So he has a long and varied background, 25 years in the industry. So let's welcome Brett to the stage.
Right here. How are you? Good to see you. Hi, everybody. Good morning. My name is Brett Cline, and I'm the Chief Commercial Officer at Codasip. Codasip, for those of you that don't know, is a European RISC-V vendor and tools provider. We're headquartered in Munich with offices all around Europe. And I'm here to talk to you today about RISC-V customization and what we like to call custom compute. So as engineers design their systems nowadays, there's this trade-off that needs to be made. Do I want flexibility in my system, or do I want the ultimate performance that I can get? And so how do you go about doing that? Well, there's this pendulum that swings from left to right, and it starts off with, I'd really like to have the ultimate in flexibility, so I use a general purpose processor, and that gives me the ability then to change my algorithms at any time and have flexibility as I'm building my overall system. But what if I really need power, performance, and area to be optimized? Well, then I go to this hard-coded approach. Maybe it's traditional with RTL, or in high-level synthesis where I spent 20 years taking an algorithm and putting it into a fixed function. But they each have their trade-offs, and sometimes I want to have both. I want to get right to the middle. And one of the great things about RISC-V is it means we don't have to choose any longer. There's a way for us to do this and achieve both of those goals at the same time. So RISC-V has been the easy way to do it. The open instruction architecture gives us the opportunity to be available around the world with no licensing and no specific ownership. The growing ecosystem, the no restrictions, but most importantly, customization is not only allowed, it's encouraged, and the ecosystem allows us to do this. So this helps us to counter the end of the scaling laws like Moore's law or Dennard's scaling or Amdahl's law, but it also allows us to have an ISA and implement this idea that we call custom compute. So if we're going off and we're designing our system or our chip, we know that there's a number of ways that we can customize a RISC-V processor to implement what's good for us, so something for our custom workload. Now, RISC-V has a bunch of standard extensions. I can use those extensions. But what if there's a way that I could go off and accelerate my algorithm and bring to my system more value than my competitors can get? So for instance, what if I'm doing an AI algorithm, and I know that there's a certain set of instructions in there that would really give me a value that no one else could get, either performance or area or power. I can go off and I can extend this by adding custom instructions that go off and implement those specific parts of my algorithm to give me an unfair advantage. It's not a one-size-fits-all world when it comes to processors. So if I'm just licensing the standard processor from a vendor, I might not get the best for my design and for my workload. This optimization space is much wider if I start thinking about all the things that I can add to my processor to not only give me the flexibility of running software in a processor, but to give me the value and the performance advantages of doing fixed function hardware as well. So in order to do this, we have to shift left. This seems to be the buzzword in the industry. So what does shift left mean? It means that the hardware team and the software teams need to start working together much earlier in the process. It's not simply about picking one processor and figuring out if my software is going to run well on it and then spending all of my time implementing the software. What I really like to do is start with my software workload and find a hardware that works specifically for me. And so this is what we like to call custom compute, or Codasip custom compute. So custom compute in itself is not new. It's something that's been around in the industry for some time. And in fact, it's actually highly rewarded if you take a look at some of the biggest companies out there in the world. I didn't get a chance to watch the keynote for yesterday, but my guess is that somewhere along the way, this company talked about some custom hardware that they've been building specifically for their application, right? So why is it that companies like Apple and Tesla, who have done custom compute and built their own types of applications and their own hardware for those applications, why is it that they've achieved so much more of a financial advantage in the industry than others? Now, you could argue that the semiconductor part is a big piece of it. It's obviously not the only part. But it is clear that somebody like Tesla, who builds something that's very, very unique and builds their own custom chips and processors inside that design, and ships way fewer cars than Volkswagen does, you could argue that maybe the silicon advantage is something that gives them a financial advantage as well. So our fundamental beliefs is that the market's changing. We clearly know that RISC-V is gaining share, and as we heard this morning, it's I think 16% in 2027. We know that hardware and software collaboration is important, and so this whole idea of co-optimization or custom compute. Instead of picking a processor and going through processor selection, now we're going to go through processor ownership. So inside of my own supply lines now, maybe I don't license IP from somebody else. Maybe I build and I own my own IP down in the future. And then we also know that OEMs and system companies are going to be doing many more of their own chips. It's very clear this trend has started and it will continue. So there's going to be big winners and big losers. So when we start thinking about this now, and someone says, oh, I want to build my own processors, well, it's not the same as it was 30 years ago. 30 years ago, companies were vertically integrated. They had their own tools, they had their own processors, they had their own CPU designers, big teams of people that would go off and build these CPUs. But that's not the same as it is today. Today, there's a scarcity of skills. So when we look back between the two of those things, there was a time in the middle where the licensing model showed up. And licensing models are really efficient. So somebody else builds a processor, and we all just license it. Well, that's great, because that gives me the advantage that I don't need to have 100 people to go off and build my CPUs. But now it runs into a problem where I don't own my own IP, and I certainly don't control it. So if we look at this scarcity of skills and we think, okay, well, if I don't have enough people to build CPUs, and I don't really want to go through a licensing model like that, what do I do? Well, our contention is that you start off and you start with some IP that you can then license and you can modify, so you can own it afterwards. So the question for you is, how has the industry coped with complexity of limited design skills over the past 50 years? Well, the answer is that automation and EDA tools help with that. There's very few people in the world now that lay down transistors, right? Because there's tools that you can write RTL code or you can write System C, and you can synthesize it, and the tools will put this in place for you. So we think the same sort of thing will happen in the RISC-V market as well. So we have technology that we call Studio, and what it allows you to do is to take our standard customizable IP, start that use that as your starting point, where there's been hundreds of engineer years that have gone into it, put that into a technology that will profile your software specifically for your workload, and then give you the suggestions and the direction on how to go customize the processor for your specific needs. And so not only does it output the new RTL that you would go off and implement, but it also outputs your entire software development kit. So your profiler, your compiler, your debugger, those types of things. But this is only one aspect of custom compute. Custom compute is not only about power, performance, and area, but it could be about different technologies that you want to implement. So one of those is this idea of safety and security. We simply can't just go off and build a processor and think, okay, everything's good. We might want to build some security aspects into it or some safety aspects into it. And so what if there was a way for you to go off and take this processor and build that into something that's interesting that deals with a fundamental security problem? Right now, if we look at security in the market, you'll know that I think it's typical that about 70% of all the problems are due to memory errors, right? So buffer overflows or buffer writes or buffer reads that are out of space. And if you'll notice that the CVE space where this Heartbleed bug showed up, there was also one recently where one of the popular devices in the world was under attack. These types of things can be fixed using custom compute and some specific security implementations. So back to my question again, well, what if there's a way that you could take a processor that's standard and you could customize it to put it into your environment that handled this very specific thing? And because you've customized it, now nobody knows what's underneath it. So the hackers don't know that you have a certain instruction set architecture in there because you've changed it. So it makes it a little bit more inherently secure, and it gives you a way to be protected by using customization in your own flow. And we think it's really cool because it's something that we'd like to talk about a little bit more, which is this idea of, well, I guess the marketing team caught me. We have this idea of a really cool security processor, and what you'll have to do is come by the booth and take a look at it. I think we've got some cool stuff to talk about, but apparently not quite ready to announce yet. But security and safety is something that's going down this direction, and I think it's something you'll find that's really cool in order to protect your own designs. So the realistic aspect of the world is that there's no more free improvements with Moore's law, right? It's just not going to get us the improvements that we want anymore. So now we have to look for other ways to go down the path of improving our performance, improving our power and our area. We like to call it custom compute. by merging the software and the hardware together and starting to think about it much more early in the process, then we can go off and start to build processors that are designed for our specific workloads. And obviously you need both the IP, so the RISC-V IP that's out there, but you also need tools and technologies that can help support that. So during the week, we'd encourage you to come by and talk to some of our experts, our CTOs at ENCS here, and talking about RISC-V on the demo theater on Wednesday, and also Tarek, our lead IP architect, will be here talking about code size reductions and another idea of customization in the RISC-V space. Or come by and check out our security stuff, or come see a demo. So thank you very much.